Recording going. So my normal computer is back, and so we'll resume protected both behaviorally and physically now, which is great. Okay. So uh we've been continuing our work through section 2.4, and particularly these four perspectives. So I'll remind us that we've been talking about presheaves from the perspective of processes, ways in which they can help us sort of model or characterize processes, as ways of extracting boundaries. That's something we'll be talking about more today, as conditions on how probes of a space relate to one another. And finally, as restrictions, which will be the subject of Wednesday's discussion. So we're going to be particularly talking about some material germane to the second and third of those today. But talking a little bit to finish up something I mentioned in the closing minutes last time, germane to the second of this. No, excuse me, the first, the processual. Okay. So first thing I wanted to bring us back to was the topic of the category of elements. We had discussed the category of elements for a category in a previous session. And you may remember it. The idea is, for a functor, a presheaf, specifically from a category to set, we have this construct called the category of elements. And it's actually a more specific example of a broader construction called the Grothendieck construction, which plays a really important role in category theory. Now, the category of elements is defined for a presheaf, where again, we're mapping from a category, shown down here, a schema category, into set. And the idea, you may remember, is that each object in the schema category maps to a particular set. Each morphism in the schema category maps to a function between sets. And the category of elements invites us essentially to erase the distinction between those sets here. So each element of each of these sets, for example, associated with X, becomes an object in a category. Each element in the set mapped to by Y becomes an object in this category of elements associated with this presheaf. So the presheaf here, morphisms in the schema are going to map into functions between these sets. And these functions constitute morphisms in this category. Morphisms that don't represent typically mappings so much as a relationship, directed relationship, say from X3 to Y2, or from X2 to Y1 and X2 to Y1, X1 to Y1 here. And there's a special type of relationship, as it were, because between this category of elements and the base category that is of great significance, but we won't be going into right now. There's a particular type of relationship down from this top category to the bottom category called an op vibration. And this is in particular a discrete op vibration because it's defined in terms of sets here. Okay. So you'll remember this? You remember this idea of the category of elements? So you may remember that we took a look at the category of elements for a set of particular presheafs. So if we had a presheaf associated with a schema category for discrete dynamical systems where we had a state and a next map for that state, then we could have for a particular functor, remember it's a category of elements for a specific functor, F, specific presheaf, mapping from the schema category into set. This is one such presheaf, right? Where we have two states, so state maps to a set of size 2, and where the next function, using the notation of CATLAB here, maps the first of those states to the second of them, and the second of them to the first. So the index here is the current state, and the value here is the next state. Yes.
I just remember like my confusion on different names of schema in software.jl. What's the meaning of free schema here? Why called free schema?
Well, the free schema would suggest that. So, great question. So the question was, what's the meaning of a free schema here? So I'm gonna stop this for a moment. And maybe we'll actually look at some of these diagrams that are already drawn. And while the computer is on this one, I'm going to move this side.
I'm waiting for Matthew to move that.
Yes. So when we have a schema, we present the schema. And in fact, the very name here refers to the fact, the very macro in CATLAB we use to define this refers to the fact that we have a presentation. Okay. And so we have the @present macro, right? And our presentation is not, we're not giving the complete category here. We're giving a presentation of a category, and that has a specific meaning. Here, what it's telling us is that we're defining the category in terms of some what are called generators and relations. And the generators here consist of a set of objects and a set of generator morphisms. There are no relations explicitly given here, none explicitly given, but more technically, what we're actually describing there is a category freely presented, which is the norm in CATLAB by this schema. And what this means is that you notice there's a morphism there, F, right? And in general, we could define relations on F, such as the fact that F, when squared equals ID, this would be a relation we could describe. But if we don't describe that relation, if we didn't have this, what we'd be saying is that by implication, this is free. This is the standard in CATLAB to say this is freely presented by that. So what this would mean is that subject to the laws of categories, except for where stipulated by the laws of categories, if you iterate F, each successive iteration will define a new morphism. So it's really all paths through this that constitute the morphisms. So we're giving here a specific generator morphism, F, but by implication, you could do FF. And the fact that it's free is saying that's going to be a new morphism. FFF will be a new morphism. But notice, because of the rules of associativity, it has to be the case that F, if we consider FFF, that it needn't matter where we put the parentheses. So in other words, FFF, if we parenthesize it as FF, composed then with F, it's the same as F composed with what? FF. So every morphism of this is is independent, but independent in a way that observes the rules of categories, which mean that it honors ID, it honors the identity morphism, right? So F identity is the same as F, which is the same as identity F. Those aren't different. These aren't different. They're the same, but subject to these laws of associativity and unitality, the unit combination without any, every iteration of this, every path of F's will be independent, will be a distinct morphism. And in general, we'd expect that for an arbitrary dynamical system, that as we iterate F, updating it, at least for a long time, it might be that the successive iterations define independent function. Like it may shuffle things around in unique ways. Now, eventually it may get in a loop, right? Where it's not that it's not different from then on out, but it's saying that every path of F's here in our presentation by default is considered distinct, subject to laws of category. So that's why I would say it's freely presented by this. Now, if we put in relations like F squared equals ID, it's freely presented subject to those relations. So in other words, we need these to hold. But then within the context of that, we might still have freeness. For example, if there were another morphism G, we might have those interacting with F in different ways that are by default free. Does that make sense? Great question. Okay, but I want to ask about this, and maybe what I'll do is ask about this with the case of a free category. So a free monoid. This is a free monoid. Okay, so this is the theory of free monoids. We map it over to get a model of a free monoid, say with particular values here. In here, maybe it's the natural numbers, for example. The natural numbers here. So we map star to the natural number, to a set of natural numbers, and then we map F to some particular function here. Some particular function that updates the natural numbers. You can imagine that, right? And there's a lot of different functions that would be associated with different functors. These are different models of this theory. Now, if we do that, we can draw out for a given one of these for a given one, we could draw out the category of elements. Right? We could draw out the category of elements associated with it. Remember, what is the category of elements here? Well, it's a category that takes into account the fact that we have this map to a natural number, and then every element of this set, of this set of natural numbers is a what in the category of elements. The category of elements is a category, and every element in this category of number, every element in this set mapped to by a function that it maps the only object here in the schema category to here. In that set, every element becomes a what in the category of elements, an object, right? So we would have objects if we consider the category of elements. Maybe I'll draw it over F somewhat suggestively. So here there'd be an object for 0, an object for 1, object for 2, object for 3, and so on, right? And what are the morphisms here? What do the morphisms represent for the category of elements associated with this functor. What do they represent here? Maybe I'll draw them to give myself more space, and given that it's a category of elements for the functor, right? So here's maybe 0, 1, 2, what have you, 3, and so on, 4, 5. What are the morphisms in the category of elements? What do they describe? The relations between these objects, between these numbers that describe. So if I draw, say, 1 from 0 to 2, what does that mean here? What would that mean?
0 is a smaller role.
Sorry?
0 is a smaller role equal to 1.
Well, okay, actually it doesn't. For the category of elements, it doesn't mean that. For the category of elements here, maybe I'll call this next to remind us. Call it next. Next. What does it tell us? If there's a link from 0 to 2, it tells us that this particular function that's mapped, this maps to, if it will map 0 to 2, right? If we're in state 0, if we have a value 0 here, it'll map it to 2. It follows what the morphism does to it. If we're in state 1, maybe it maps it to 0. If we're in state 2, maybe it maps it to 4. Maybe from 4, it maps it to 8. Okay? Something like that. Maybe I'll make this, make it a nice little, I'll make this 0, make it 1. Something like that. Maybe 3 gets mapped to 2. Maybe 5 gets mapped to 4. Maybe 6 gets mapped to 2. Maybe this gets mapped to 8. So maybe here we double the number. We double it if it's a power of 2. And we round it down to the nearest power of 2. Something like that, or to the next lowest power of 2. You have to think about 0. Anyway, the point is, this describes the evolution of a dynamic system. This category of elements. The fact that there's a morphism in the category of elements for this functor from 2 to 4 says that if we have the value 2 here, it is mapped by next to 4. And again, this is a category, and it has composition. So if you have one from 2 to 4 and 4 to 8, then there's a morphism from 2 to 8 that comes from iterating next twice here. Next. If you started with 2, you'd get 8. Here, that's reflecting the fact that you go to 2 to 4 to 8. Okay. So the category of elements describes the evolution of this system. And that's what we saw associated with page 'Page, for example, page 68. It's showing A, B, C mapping, and that's showing how they are mapped from this schema category shown on page 67, which is this one. So here, this is a free monoid, but we can interpret it as the theory associated with discrete dynamical systems, where this says how the system evolves in the next period of time. Like what state it goes to in the next period of time. And next reflects a state update. Now, I want to highlight that on page 66, we have the category of elements shown for a different category, namely the category whose indexing category is given by B here on page 67. So here we have the index. This is again piece theory 3 example. So the indexing category here has, it showed we have sort of a point object, which I think is called V later, and a loop object, which is suggestively shown like that. But basically, there's a morphism here from V to L. Maybe I'll just draw it as V like L, and it's called I in general. Now, this is going to be B, and in the book, Daniel Rosiak considers B op, which is a map from this to set. What is B op there? L to V, right? So B op is just L to V. And if we map that into set, we get something, if we call this X, we get something that maps X of L to X of V, right? So it maps for every loop what its center dot is, right? And what's shown here is we could consider the representables for this. What would the representable be for this category? Well, we have to be careful. Are we talking about B op? This is B. This is B op here. If we're talking about B op, what's the representable for that? What would the representable be? So let's consider it. So we're considering, actually, let's not talk about representative. Let's talk about the category of elements first. Sorry. Category of elements. So if we have this, what would the category of elements look like for a given functor here, functor X into set? What would it look like from B op into set? Well, we'd have something like this where we have a functor. There'd be an object in this category of elements. What would category of elements look like for E elements of X? We're calling it elements of X. We'll erase this. We consider elements of X. What would they look like? Category of elements for a given functor X. There'd be, what would the objects be? Objects would be all of the elements of the set. Do you remember our diagram for a category of elements? It's this one right here. I'll put it up on the screen again. Here we go. There's a category of elements. Remember, every object in our category, B op, we have a set, right? It's mapped, every object in B op, it maps to a set, right? So we have a set of L, we have a set of V, and each of the elements of those sets turns into a what in the category of elements for this functor X. Each of the elements of these sets, namely X of L and X of V, turns into an object in this, right? Right? So it's kind of like we have a bunch of L's here. Maybe we'll call them. Well, we could call them, judging by the picture on page. I'm seeing if there's a nice smaller label example with this, but maybe not. Okay, let's consider the little example on page 65, where we have these nice little diagrams. What are L here? Well, it's alpha, beta, gamma, delta, and so on, right? So this is like alpha, beta, gamma, delta, epsilon, etc., and so on. And what else is in the category of elements? So these are objects. What else is in it? Yeah, the vertices. And what are they from this diagram on page 65? A, B, C, D, right? A, B, C, D. Now, are there morphisms in this category of elements? Well, there's identity morphisms, so that is true. There's always identity for any object. But what else is there? Well, remember the category of elements has for every morphism in its in the base category, in this case, B op.
Okay, for each loop, find its
For each loop, it finds its vertex. So let's go back to this. So for loop alpha, what's its vertex? What's its center vertex?
Alpha, where?
In C. For loop beta, C. Loop gamma, C. What's how about loop delta? Turns out it's D. Appropriate name now. Loop epsilon, D, etc. So this just picks out the appropriate one. Are you okay with that? Now, what I'm telling you here is that this provides a way of drawing any functor out diagrammatically. We could show it. Presheave functor. Any functor into set. We can always form the category of elements of that functor. But often we have diagrammatic convention, and we wish to show them pictorially, like we do on page 65. And Daniel Rosiak's comment here, you'll notice on page 66, he's showing these mappings on page 66. What are those mappings? What is it that's being mapped into these pictures on page 66? There's these shapes, these things he calls figures on the left. What are those shapes? Those are begins with R. Those are the representables.
Yeah.
Those are the representables for this. And remember how we figure out the representables here? You remember how we figure out a representable here? So for B op, how do we figure out a representable?
But have two objects.
We have to consider in B op. Yeah, okay, good. For a given object, let's say we have to consider the representable for L and the representable for V. Let's consider the representable for L. Okay, so representable for L, we have to fill in different things for this,
Yeah.
right? Different objects, just like you just said. So L, how about L to L? What's the set of that? What's the set of morphisms here from L to L?
I think
What's the set of morphisms from L to L? Identity on L, right? And what are the set of morphisms from L to V? Well, it's really comes down to F, right? So what is that? What's the representative? So this is some sets, and we have we also have a lifting of the morphism F, which is just going to be F after identity of L. And this, what's that?
it's still out there.
It's still, yeah. That's right. Actually, it's giving me a map from, technically, it's a map from the morphisms over L, IDL. It's giving me a map from them into F composed with them. So it's going to be them and then after S. So this is a function. It's going to turn each of X of L into X of V, right? So what does this look like? What I told you last time is this representable is itself a B offset. It is itself a member of this. Appreciate this. It is itself one of these diagrams. What diagram does it look like? What does it look like as a diagram? It has one center point and it has one what?
Well, identity ones.
It has one loop. And it has one vertex. Remember, this is a functor. It maps, it takes for each element of the source category, this guy here, it takes it to a set. So it's saying this is the set of loops. This is the set of loops here, right? Where we plug in L to this. This is a functor mapping objects in the source category, V and L, to a set. So we plug in L into this and we get this set. So how many loops are there in this B offset? There's one. How many vertices are there in this B offset? One. We map this into this. This is a functor mapping from this category into set. Maps this guy, the object here, to an object in set, which is this one here. Maps V to an object in set, which is this one. It maps F to this function in set, morphism in set. And what I'm telling you is that mapping is itself a B offset. It's itself one of these diagrams that's shown, one of these things. And what does it look like? What's that diagram look like? What does the little picture look like associated with this? How many points does it have? How many things does it have at its center?
Was identity one.
One.
Huh?
Well, you go. How many ways of going from L to V, right? We're considering the representable for L.
L.
This is representable in this category for L in this category. This being that one,
Mm,
right? Right?
Yeah.
That's representable for L. What does it look like? What is that? What does that look like? What does it look like? It is how many loops?
Okay, one
One loop.
one vertex and one loop.
Right.
Is that good?
Yes. And that's exactly what that is.
Mm.
Do you see that? Okay, what's the representable for V? What's the representable for V here? Think about it. What's the representable for V?
V is identity and VL is empty.
Good.
And
Good.
VL.
Okay, so maybe I'll help by drawing it out.
Yeah.
Here's L, here's B up. Here's L, B. Right? And we're considering that this, we're imagining this for the representable. Here's gonna be our set,
Mhm.
right? Right? This is gonna be our set. And we're gonna consider here. This is gonna be a functor. What's the functor gonna be? It's gonna be B op L comma this. And so here L will map into. L maps into, well, keep it at the same picture. L maps into some set, right?
Mhm.
V maps into subset itself, right?
Mhm.
Objects to objects,
Mhm.
morphisms to morphisms, there's some function.
Yeah.
What is this object to which this maps in? It's IDL. What is this? What is this object to which this maps in? What's the set this maps to? IDL. What's the set this maps to? F. What is this morphism map to? Let me put this down here. B off L. So we're considering the representable functor
Mm.
for L for this particular capital. What does V map to? It maps to F.
It's identity and composer.
And this one maps to this morphism, maps to morphism itself. What's morphism said? It's a function.
Yeah.
It's X. Go to F after X. Are we okay with that? And what I'm telling you is that this is a Biop set. And what is a Biop set? It's one of these figures. And which figure is this one? It's this little loop
Mhm.
with a thing for the blossom, for the bouquet. It's a blossom, single blossom. Okay, now let's consider Biop. Same thing. Here we go. And now let's consider set. Same thing. This is we're gonna have some sets here. L is gonna map into a set, right? This is the same category Biop, but it's a different functor.
Mhm.
This is gonna map to here. This is gonna map to here. Morphism to morphism. But what functor is it we're showing here? This functor that we're showing is. Knock this over. I'm just showing this as a functor, so I'm giving it a nice name. What functor am I showing here? B of V, comma dash. Right? So that's borderline unreadable. Maybe it's fully readable. B op V, comma dash. This is, what do we call this? This is the what? Representable for V. What was this? For L. Okay, so you tell me, if we consider what are the rules for these sets are, what are the set of all ways I can go from V to V? What's the set of all ways I can go from V to V here? Identity on V. What are the set of all ways I can go from V to L? Empty. I'm just gonna, I'll put it close together. I could put it over this. And this is just, it's the unique mapping from an empty set in any set. So what does the representable look like for a point?
It's one dot. Because of
Just
what-
a dot.
one second of what-
And this is exactly what he shows. You see that?
Mhm.
Okay. So now this is incredibly powerful. You probably don't realize it, but these representables are, I told you last time, the building blocks. They're the building blocks here. And I'd like to talk about I'm moving that. Okay. So let's talk about these things. Here we go. So we've been talking about the category of elements for schema. We sort of talked about what those are for that and how those can be used to form these diagrams. Now I want to talk though about the implications of these representables. Okay. So I'm telling you that these representables make up all of our presheaves. Presheaves are made of coproducts of representables. Okay. So we've just gone over the reasoning for this, right? Hom functors, right? And what I'm going to tell you here, I'm not going to go through the details, but any C set can be decomposed into a co-limit of representables. These were from discussions with John Buys in Edinburgh. And basically, I won't talk about it, but for those who have seen some math before, I don't know if any of you have seen like Fourier transforms, or if you remember dot products of vectors. Remember, what do you do for a dot product? If you have a vector 1 of ABC and another vector of, DEF, how do you take the dot product?
Summation of product of
Summation of product.
summation of pairwise.
That's right. And do you remember what you do for Fourier transform? It's the same basic idea. You actually take the integral of the dot product of the signal you want to take the Fourier transform of over time, say, with sinusoids. And you integrate up. Instead of summing up, you integrate because it's continuous. Well, that's what we're doing when we take any C set, F, it's a C set, map from C to set, we could take its kind of dot product with the representables and sum it up. And we will find that it has pieces, components for each of these representables. This is like taking the dot product with a vector, right? You have a vector and you take the dot product with another vector to get how much of that other vector is in that first vector. The projection, yeah. So if you have vector V, I could take the dot product with another vector A to get how much of A is in V, right? And I could do it with another one, and I could do it, with a set of orthogonal ones. That's what this does. And I'm not going to go into it, but it's using something called a co-limit, which we'll be learning about. And basically, you can decompose any C set into a sum of representatives, a co-limit of representatives. It's actually not just a sum. Sometimes we have to stick them together by identifying objects in them, identifying particular sets of things within each set. So we have to, it's like the Tinker toy, we have to stick it together. It's not just A co-product will be just laying the pieces of the Tinker toy side by side, as John By says. A co-limit is like sticking them together, like gluing them together, sticking one together, identifying pieces. Okay. Okay. Now, right. So, yeah. And you can show that some of these require co-limits of representables, not just co-products of representables. Some of them can just be a co-product of representables, but some require an honest to goodness co-limit. Okay. But here's the thing I want to talk about, and this is really useful. This features centrally in our algebraic ABMs. Okay, here we go. So I'm not going to give you all the details. If you really want to read a beautiful treatment of it, I'd invite you to read chapter 23 of Joy of Abstraction on Unida. But here's the thing. This is something I do want you to know, and it's relevant for this chapter, 2.4, this notion of a probe. Okay. So the idea with a probe is that, do you remember this idea of functors as finding patterns in a target? Do you remember that? We kind of started with that with functors. We said, like, find me a walking edge in a category. Do you remember that? Like, we had a category here has different morphisms in it. Remember that? Something like that. And then I said, like, now imagine this as another category. So this is category D, this is category C. And now this is the walking arrow. And then there's a functor for every match of this to that. Do you remember that? Do you remember that idea? I'll show it. Oh, am I not showing my screen? Oh, no. Not showing my screen. Well, I might as well show the board then. Here, right? Now let's show the screen. So, did I miss anything? No. Okay. So there's a key result called the innate limit, which is incredibly deep, and many people argue it's the almost had a panic attack. This is on there. Some people argue it's the single most insightful thing that's come from category theory yet. But the Unida lemma says that if you consider a representable for an object, not just any category here, it concerns maps between C sets. Okay. So for the Unida lemma, we're going to be concerned with, we're going to have a C set F. This is some C set for some schema category, right? And we're going to consider maps from representables. So this is we have some indexing category. So the schema will be C op. The indexing category will be C. And we're going to consider cases where we have this thing here. Maybe it's a database of people, their dogs, and their homes. Maybe it's a graph. Maybe it's a symmetric reflexive graph. Maybe it's a bouquet of these little loops and, you know, these little things like this. It might be a picture of it. And then we consider a map from a representable here into it. So this is a C. This is going to be also a C op excuse me, this is going to be a representable. So it's going to be a representable for a particular object in this category. Call it little c, from C to dash in this category. So it's gonna be some representable in the category, like those we just derived. And now we're going to consider maps from this to this. We're going to find this pattern in here. Okay. We're going to treat this as a pattern to be found here. This is a category. It's or excuse me, there's a here this is actually a functor, and we're considering mapping from this functor into this one. That's right. This is actually a natural transformation. And we're going to find instances of this representable over here. And what the innate lemma says is that if you find instances here of this, maybe it's a little loop, this one. So you'll see the idea here. It's exactly what's shown on page 66. If this is a representable here, say this loop, and we try to find all instances of it in our functor f, which has multiple bouquets, let's say, some with 2 loops, some with 4, some with 1, some with no loops at all, some with 10 or whatever. If we consider this, the number of possible matches of this into here is proportional, or is in one-to-one correspondence with the number of these objects within this schema. Okay. So essentially the size of the set of these morphisms, of these mappings, of these findings of this pattern in here will be proportional to the number of places they occur in here. The number of them, right? So this functor, if we consider, C is in C, right? C is an object of C, of capital C. Little c is an object of capital C. Maybe I'll call it, instead of C, I'll call it, what do I call it in this one? X. I'll call it X. Okay. Here we go. We'll call it X. To avoid saying C and C. Okay. And then, okay, so C is some object of X. This is the representable for X. You may remember that representable. It's just what we derived, right? For the bouquet. This is the representable for L. So in that case, X would be L, right? This one right here. You okay with that idea? And what I'm saying is, that's a functor, right? That's a presheaf. This is a presheaf of a diagram, just like the one shown on page 67. Just this one here. That's a C set also, right? It is some number of dots, it is some number of loops, but it also has this relationship between the loops and dots that says for each loop, what's its central dot. Are we okay with that? And it's shown here. We okay with that? What I'm telling you is that the number of matches here, the number of places you find this pattern within this C set is in one-to-one correspondence with the number of the size of the set of X's here. In other words, if X is L, the number of, this is a mapping from C up to Z, so it maps, F maps X to some set, right? I mean, that's what F does. F maps objects to object. This F maps objects to objects, right? It maps objects of C. So it's gonna map X, which is an object in C, right? To some set, right? This set is F of X, right? This is the set of L's in here, right? This is a functor from C up to Z, so it is a set of L's. Let's draw it out. This is a functor from C up to Z. We'll draw this one out, right? Here we go. Here we go. We'll draw it out. So here's our C op. C op is, where is it? We called it B op over there, but that's fine. It's L to V. Here we go. L to V. Just like that, right? This is C op. I'm drawing this functor out. This is like, just to make sure that we're all on the same page. This functor is from C op to Z, so it maps from this over here to Z. And just like over there, it maps L to an object in set. What's an object in set? It's a what? Set. Maps V to some set here, right? So let's call it F. This is F, right? It maps L to a set F of L. It maps V to a set F of V. Are we okay with that? It maps this morphism. What do we call it? F. What do we call it? F. Maps that to a mapping here, which says for every loop, what's its vertex? What's its center vertex? Are we okay with that? So I'm telling you, this is one of these. And therefore, it has a set of loops. And it has a set of vertices. Are we okay with that? It has a set of loops and it has a set of vertices. How many loops are there? Well, I could count, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. And then I said I did 10. 19. Okay? There's that many loops. Are we okay? And what the innate lemma is saying is that for every one of those loops, L of X is L here. So if X is L, then those loops, F of L, L to this set F of L, is in one-to-one correspondence. There's one of them for every one we find by mapping the representable into this. So what I'm saying is that if I map the representable for L in, which is shown here, for L, I will have a number of matches exactly equal to. In other words, I will find each of these L loops. So the way to find the loops is by mapping in the representable. The way to find the loops. The way to find the vertices is by mapping in the representable for loops. The way to find the vertices is by mapping in the representable for what? Vertices. If this were a functor of people, dogs, and homes, the way to find the number of people, or the way to find all people in this set, in this C set, will be to map in the representable for people into here. And I would find them. I could find them in this C set. So maybe that will help you understand why it's shown on page 66 that there's a match. for each and every occurrence of the loop in the right-hand diagram there. Right down here. There's a mapping from this loop here into that. It finds this representable shown on the left, this little loop, in this diagram on the right. And that finds them in one-to-one correspondence. There's a one-to-one correspondence between the number of such loops and the number of maps so far. Do you see that? Now, this is not all of the implications of innate alignment. In fact, there's beautiful renditions in terms of isomorphisms. This is just one little glimpse, and I haven't done it justice. But it's a powerful thing. Similarly for dots, if we want to find the number of dots in this diagram, we just map from the representables for dots here into this diagram, and they're in one-to-one correspondence. These maps over from this representable for dots to the occurrences of dots in the diagram. Do you see that? So what I'm saying is that representables, far from being just sort of curiosities here, just sort of curious constructs, curious C-sets, as it were, that we can build. They at once form these kind of basic building blocks of all C-sets. I showed that just a few minutes ago. Well, I showed it, maybe about 15 minutes ago now, where any object could be described as by decomposed into these representables. I didn't give you the exact mechanism to do that, but it involves these, what I believe will be a coend here. And essentially, it's like taking the dot product of it and summing it up to get how much of each representable is in there. I'm telling you that these representables are key building blocks, the key building blocks of presheaves, and that by sticking together either as coproducts or as co-limits by gluing them together at common points, like one here glued together at this point, this one glued together with this one at this point, whereas co-products is just going to put them next to each other. Well, they form building blocks we could describe any C-set out of. More than that, they provide this way of finding patterns in the target. Mm-hmm. So here, if I could try to illustrate this, this is one of these, if we consider the category of C-up sets, these are natural transformations between these presheaves, between these C-up sets. This is a representable for A, right? And I'm telling you, if we consider a functor F, we did here, in which we want to find A's, the number of places we find it, the number of homomorphisms here from this presheaf to this one, number of morphisms, is in one-to-one correspondence with the number of occurrences in here. So here, the number of A's in F, in other words, F of A, this said F of L or F of V, the number F of A is in one-to-one correspondence with these matches. This is how many times it found a match from this to this. Just like here, it's in one-to-one correspondence here. Here, B was found one time in this. So here there are two of them. Here, this is found one time. This is the representable for B in C, is found once in F. This is a homomorphism here between one C set and another. And that's what we're doing here. We're taking homomorphism between this C set and other, finding occurrences of this in here. Just like early on, we were finding one index category through diagrams. This was called a diagram, finding instances of the shape in this target. Here we're finding this shape, this sort of type of thing within this. And they're in one-to-one correspondence with the number of occurrences. So we're finding the shape for L, they're in one-to-one correspondence with the L's in F, or F of L, which is the set to which F maps L. So here, these representables form not only these building blocks, these key pieces into which any presheaf is decomposed, but there's this deep result that if you search for the representables, you hom the representables in, you do a homomorphism search from this representable into F, you find all of the occurrences of the A's. Okay. Now in the book, and I realize I'm going late here, so we'll stop for office hours shortly. But in the book, leading up to this page 55, or the example 55 rather, one of the things that's talked about is this idea of a probe. And here, what we could think of these searches from these representables as probes. These are kind of, how do we find occurrences of the loops there? How do we find occurrences of the dots there? And the idea is, if we want to find out about F, and we have these ways of kind of searching for different things in it, like we are doing up here on the board with searching for one presheaf and another. If we have it from this one, and if we have it from a dot, and a richer category might have it from other things. And then if we have ways of relating these two, then we start to get an understanding of how these are related, sort of what is in here. We can start to relate what we have in this, or figure out what we have in this presheaf F, this big presheaf F, by the number by finding these different things in it and relating them to one another, such as by going from a loop down to its corresponding dot. So here I'll just draw this. Here maybe we have a probe of dots into this. This is the representable for, so I'm particularly drawing here the representable for L here. So I don't know why I put down L underneath it, but we would write this as HL, or Yoneda sub L, Yoneda of L. Here we have this for, call it V. And what I'm saying is, if we find these, this is a probe of this into this. This is a probe of this into this. And then if we know how to go from this to this, to go from one of these, we can go down to, you just go down and find its dot associated with it. Then we start to get a view of this in 3D, as it were. We can view it from here, relate these two, we start to get a bigger picture of what's going on here. And that's
World with home search is called search.
Yeah, this is like a hom search, but this is like relating this hom search to this hom search, according to the structure here. And what the idea is that this starts to illuminate what's going on here. This starts to give you a picture of what's going on here. In this broader category. And this is the broader perspective that category theory offers, like more generally, that actually all the information about in any category, all the information about a given object, like everything we could want to know about an object that we can know about it is actually indicated by how it relates to other things. And so there's this notion of it's really how things relate to it. It's this kind of notion of like, you know, a person by the company they keep, you know, a person by the people that they hang around with, or the types of activities in which they engage. And the idea is this object, it's all the information we need to know about it is summed up by how other things relate to it in the category. And because, well, we'll see, but if it has certain characteristics, they're going to come out in the ways in which it relates to other objects. Here, it's a similar idea. We can learn about this by how other things relate to it, with the representables being particularly key things in terms of probing into it. And then we have to relate these things to one another. This is going to actually have a lot to do with sheaves. Because with sheaves, we have these different views of the world for maybe different areas of a topology. And between them and how they relate to each other, we can figure out what's going on in the underlying situation in the world across this topology. Okay, so yeah, those were okay. Yeah, and there's one final thing I just want to point out. So the other second perspective, which Daniel Rosiak offers as extracting boundaries, I want to show something about that as well. Maybe I'm going to keep my comments very brief about that, but here. This also is very common reasoning that comes up in sheaves, even more basic. You'll notice that this is the schema for what? Can you recognize? For what?
Yeah.
Graphs. Right. So we map it over as a C set. E maps to a set of edges. B maps to a set of vertices, right? Source maps to a function that says for every edge what its source vertex is, right? Target says for every edge what its target vertex. And I want to draw your attention to the fact that E to V, you could think of this as like going down in dimension. It's like for a given edge, what are the two vertices on either side of it, right? So if we have an edge, we can pick out the vertices that are on its, forgive me for speaking crudely, but on its left and on its right, if we drew it out, right? Or you know, its source and its target. So we're finding the boundary of the edge is the terminology that Daniel Rosiak is introducing here. This is a boundary. You know, every edge has two boundaries. Are we comfortable with that idea? Okay, let's take that for this Daniel Rosiak's example here with loops and vertices. Every loop has a kind of boundary or a lower dimensional kind of core. And we're kind of finding its boundary, as it were, here. We're finding its core. We're going down a dimension from it to find its like center point. Are we okay with that idea? Okay, let's build on this for some other cases. So I want to look at reflexive graphs here. Here we go. You may remember this. Do you remember these ones at all? So this is for a, well, actually, do I have a reflexive? No, reflexive would be even easier. This is for a symmetric graph. Do you remember this one? So what does inv do here? Do you remember? If I have an edge from X to Y, so I have an edge, right? The source
Arrow location.
What's that?
Changes
the arrow location. Beautiful. Okay. So for every map from X to Y, I have another edge. Sorry, for every edge from X to Y, I have another edge that goes from Y to X. And that's what these relations say. Do you see where it shows relations? So if I start with an edge and I take its involution, so I flip it around. So if I start with an edge whose source is X and target is Y, and then let's suppose I have that edge and I flip it around, then I get something so I flip it, its source is going to be the target of the original one, Y, and its target is going to be the source of the original one, X. Does that make sense? And moreover, what's this first condition saying? What's the first one saying?
Decompose involution with itself, and you just get the same arrow back.
So the flip of a flip is just the original arrow. If you flip twice, right? Like if I flip, then I flip again, I get back to the original arrow. Does that make sense? Okay. So what I'm telling you is that these maps here are like finding the boundary of this symmetric edge. It's like finding the boundary of this, it's almost an undirected edge because they always come together. They're always in both directions. So I'm finding the boundary of this one I drew on the board, right? This one right here. The boundary it goes down to is X and Y. That's the boundary of this object. Are we comfortable with that? And similarly, although I won't sort of dwell on it, I just want to highlight the fact that, like for symmetric reflexive graphs, where we additionally have this thing where every vertex is associated with a little loop of its own, sort of a self loop, as it were. So it has its own edge to itself. There, we also have this boundary map down from E to V, right? So often we will have these morphisms that find the boundaries to things. And one of the things that Daniel Rosiak introduces on page 78 is start and discusses some on page 79, starts to get into higher dimensional structures, where you might have like a graph, and in addition to edges between vertices, you have a way of mapping edges to edges, sort of a connection from one edge to another, or something like that. And actually, sorry, I need to draw this. Those edges have to go in the same direction. Flip it around here. So we can only do, like, if we go here, I'll call it A to B. And we have another one like this. This is why it's called globular. You can have like an edge, sort of a higher dimensional edge that connects these two, and it sort of unites things. And those are going to have certain properties, like if I take this, the source is still the same. The target is still the same as it was. That's why it's called globular. It's kind of this little blue sorts, and I can sort of link these up. And it turns out that in this little category that he talks about, and this is definition 54 with this diagram, where he defines these n globular sets, but he then describes it as a presheaf category. And so here you might have this, but then ultimately you might have ways of relating these to each other. Like you can have these maps. So remember, these two like map from A to B. This can go from this map, call it I, to this map, sorry, to this edge I, to this map J, sorry, this edge J. And then we can have higher level ones yet, which might map from one of these to one of these. So these might be, I don't know, call it M. But observing the fact that if I do this, the source has to be the same and the target has to remain the same. So here we have these kind of little globular structures that we can describe, sort of higher level graphs, as it were. Graphs which not only have vertices and edges, but which have edges between edges, or sort of map or sort of ways of bridging edges, and bridges even for those, etc. And each of these things here, these morphisms, that you can have from a for these successive mappings are going down in dimension. So we might go down in dimension from this one M, find its source. Well, its source is this one. Let's give this a nice name. Maybe I'll call this actually M, and then I'll call this N, and I'll call this P. So if I take P and I take its source, I'll get M. If I take P and I take its target, I'll get N. If I take M and I take its source, I'll get what? I. If I take M and I take, so this is source, target, its target will be J. N here, this one, its source will be what? I also, sorry, this is J, and its target will be J, right, and then J's source will be what?
A.
A.
Like change rule.
What's that?
Like a change rule.
Yeah, so you can see there's actually quite a lot of structure here. Like its source is also A, its target is A. And if you're wondering why, like underneath this, there's these rules. Well, it's capturing the logic of this, that like, look, if I take something here, let's consider one of these, and I take its source, so the source so if I start with one, let's say here, and I take its source, and then I take the source of that has to be the same as taking its target and considering the source of that. So it's kind of a weird structure, but it has the flavor of, I won't draw all of these out, but it has the flavor of always mapping down to boundaries. So you like map to the boundary of it. You map. So this guy is mapped to its boundary. This guy is mapped to its boundary. This gal is mapped to her boundary, etc. Boundaries. So each of these sources and targets here, sort of along the way of what Daniel Rosiak shows in that picture, goes down a dimension. And where we're going to see this is an extremely practical. There's probably some practical uses of it, but I'm not aware of that off the top of my head. These are new to me. But where this is going to come really in spades is where we have things like edges A, B, C, and we can have higher structures. So we'll have a simplex for, so this will be like a 2 simplex, and its boundaries, it'll have boundary maps. It'll have 3 boundary maps because it's 2-dimensional in a triangle. So it'll map to, its boundaries will be AB, the edge AB. So I'll call this, I'll call it T. And maybe I shouldn't call it T, maybe I should call it R, because T sounds like target. So R will have 3 maps down to its edges, and it'll map from R down to A. And maybe if you forgive me, maybe I'll just use a notation that's common. A, B, C is the triangle here. This is not specifically to be interpreted as a set, but as the object. It maps down to AB. That's 1. BC is another. That's another edge. And another edge is AC or CA, we'll say. CA. And each of these can map down with 2. This is because it's a triangle, it has 3 of these. Because it's a triangle, right? This has 2 of these because it's an edge, right? And this will map down to source A, target B, source B, target C, source C, target A. And here there's also structure like here, but it's a little bit, yeah, we'll see where it comes from. But basically it captures the fact that this is B and this is B, this is C, this is C, is not, and that this is A and this is A, is not an accident. Like there's a lot of structure here. And you can have higher dimensional structures like tetrahedra. This is called a simplex. And we can have and simplex. This is a 0 simplex. This is a 1 simplex, the edge. This is a 2 simplex. And you have these sort of boundary maps. They map down to the, from the 2 simplex to the 1 simplex to the edges, from the triangle to the edges, and the edges to the vertices. And you know, there's 3 here, 2 here. This one only had 2 at each point. Source target. Okay. Anyway, those are pretty good. that was important to say. Yeah.